Hey folks, thanks for joining me here on YouTube. I'm absent today, so you are going to see me go through a lesson, and I'm going to ask you to take notes as we get through some new stuff and then practice. And you'll have options for how you do your work after this is over. So feel free to speed up the play, pause when you need, do whatever you want on YouTube. Last week we had covered series circuits, and we came up with the following three rules for voltage, current, and resistance. All the voltages add, all the current is the same everywhere, and the total resistance is what you get when you add up all the resistances. Ohm's law always applies to everything in a circuit individually and to the entire circuit. Parallel circuits, you completed that lab last week, and we haven't had a chance to talk about it, but you are all coming to the same conclusions based on what I see in your labs, and so here they are. In a parallel circuit, the voltage of the battery is also the voltage across each individual resistor in parallel. The current splits, and so the total current coming out of the battery is divided between each of the paths along the parallel circuits. Then we get this crazy rule for resistance, that the inverse of the total resistance is equal to the sum of the inverses of the resistors in the circuit. And so at some point we will talk about, like in this lesson here, we'll talk about why that comes to pass, and so we'll do it using some new ideas. So you have those in your lab, but I have your labs right now, so you can write those down. Next part of the lesson is known as Kirchhoff's rules, and so Kirchhoff's rules are two rules that someone came up with for understanding and explaining why circuits behave the way they do. And we're going to focus on these later. They can explain every single circuit we look at on these two simple rules. And so we're going to start with the one that's called the junction rule. This is generally the easier one to understand. Kirchhoff's junction rule has to do with the idea of conservation of charge. So a circuit is a closed system, and so all of the electrons that you have in the circuit when you connect it for the first time, that's how many electrons you have. So the rule says that the total charge entering a point in a circuit must equal the total charge leaving that same point. So what I want to do is just show you how that works with a series and a parallel circuit. So here's one of each. So the total charge entering a point in a circuit must equal the total charge leaving that same point. So we're going to focus on that point right there. I can choose any point I want, but I chose that one. And so what I want to understand is that in a circuit, the current leaves the positive terminal of the battery, and it travels all the way around the loop until it gets back to the negative terminal of the battery. So if this is the point that I focus on, there's a certain amount of current that's going through into that point. Now that current just passed through this resistor, so we're going to call this I1. And then after that point, the current will continue through that path. And so that current is going to now go through I2, and so I'll just call that current I2. Great. So I've chosen a point, and I1 enters that point, and I2 leaves that point. And so what Kirchhoff's junction rule says, and basically what the conservation of charge says, is that the electrons can't just vanish once they get to that point, and they also can't, like, that point doesn't make electrons. And so the total current that goes into that point has to equal the total current coming out. And so I can write the following relationship, that the current that went through R1 is going to be equal to the current that went through R2. And this is the same idea as our series circuit rule for current, that the current is the same everywhere. And so, you know, if I extend this to the rest of the circuit, no matter where I pick on my circuit, it's always going to be the same current. It's called a junction rule because it really comes into play when current divides, takes a couple paths. And so there's no way for the current to go anywhere else, so the current has to be the same. For a parallel circuit, I'm going to very specifically pick this point right here, because it is a junction. And so I'm going to draw my current arrows again. So going into that intersection, now that current is the total current that left the battery. And then leaving that point, there's actually two roads. So there's the path that goes to our left, out of that point, and there's the path that goes to R right out of that point. So on the left, we have the current that's going through I3, or through the resistor marked 3. On the right, there's a current going through what's marked 4. And so this is truly a junction. This is actually what Kirchhoff's rule is really for, is that whenever there's an intersection in a circuit, the current has to split. So all the electrons that go through this top wire, they are all of the electrons that are traveling through. When they get to this point, they can only go left or right. So if an electron goes left, it can't go right, because it can't be in two places at once. So I can write the following relationship, that the total current that goes into that point is equal to the current that goes through 3 plus the current that goes through 4. So this junction rule is the one that actually shows us why the series and parallel rules for current are the way they are, that we get that junction. Okay, moving on. Next one is Kirchhoff's loop rule. And this is the only other rule that we'll cover of his. This one deals with conservation of energy. This one's a little trickier to understand, but it's not too bad. Basically, conservation of energy, the idea is that any circuit we build is a closed system. And so the total energy of the system has to remain constant. Now, electrons go through this kind of roller coaster where in the battery they gain energy, and then all the way through the circuit, as they go through the various loads on the circuit, they lose energy. So for any complete loop in a circuit, the total rise in voltage from the battery must equal the total drop in voltage from all the loads in the circuit. And so I'll show you how we use this one. So again, we have two circuits, a series and a parallel. And so I want to focus on loops here. So for the series circuit, it's pretty simple. There is only one loop. And I'm going to draw this in really broad terms. I'm going to say, oh, well, this loop looks like this. That's a complete loop in the series circuit. Now there's the battery. I will actually label that VT because that's the total voltage. So what the loop rule says, for any complete loop, the total rise in voltage has to be equal to the total drop in voltage. So the battery is there to give energy to electrons, and so they have a positive voltage, they have an increase in potential, or an increase in voltage. As they go through, the various things take away some energy from the electrons. Now, the wires, we imagine, don't do that. So really there's just the resistor marked 5 and the one marked 6. And so according to this loop rule, the voltage that goes through 5 plus the voltage that goes through 6 has to equal the total. And so that's why we say in a series circuit the voltage gets like shared among things. Now, just to show you like what else could happen, if I added another resistor over there, and we said, oh, well, that one's now going to be, we'll call that one resistor X. This equation would change. The total voltage wouldn't change because it's still the same battery. Now, this total voltage would be equal to V5 plus V6 plus Vx. So the more resistors you have in series, the further and further the voltage gets divided between them due to the loop rule. Okay. So here's our parallel circuit. And so I'll do this again visually. I'll mark this VT because that's the battery. There's a loop in this circuit that includes the resistor marked 7. Now, the resistor marked 7, it doesn't share anything else in its loop. Its loop doesn't have anything else in it. So I can write an equation that says the total voltage is equal to the voltage that goes through R7. Because R7 is the only thing on its loop, it doesn't have to share the energy with anything. Whatever energy the battery gives has to be used by the electrons going through R7. There is a second loop, and that's not showing up so well, but I think you'll be able to see it. There's a second loop that goes through R8, and I don't really have another good pen for that, but that's okay. So there's a loop that goes from the battery through R8 and then back to the battery. So I can write a separate equation. I can say the total voltage is also equal to the voltage across 8. Because 8 is on its own loop, all the energy that's given by the battery has to be used by R8. And so in the loop rule, I get that the voltages in a series circuit add, whereas each thing in a parallel circuit has the same voltage as the total. So that's the end of like the main lesson. So you can, I recommend if you're like not done with everything, if you still have to do the lab or you have to do 9.5 or 9.6, that you now go do 9.5 and 9.6. You can definitely come back to this video, but if you don't watch the rest of this video, you'll have time to do this in class on Wednesday. So you can pause or stop or do whatever you want, and come back to like the 11th minute of this video when you're ready. But I'm just going to keep going. The last part of this is equivalent resistance, and I kind of messed up on this, so I'm going to scramble here. So this is going to be something that we'll do in class, and if you want to get a head started on it, you can. Equivalent resistance is something that's an intro to our final topic, which is combination circuits. Whenever you set up a group of resistors, they will have a total resistance based on the rules by which electricity works. So we have a series and a parallel rule for resistance, and you have access to that. So equivalent resistance is like imagining if I had like 17 resistors set up in a circuit, what if I replaced them with a single resistor that had the same resistance as the total? And so that's kind of the thought experiment there. So I'm going to go through this kind of quickly, but it really just uses the two rules for circuits. So for example A, these two resistors are hooked up in series. So the equivalent resistance is going to follow strictly the series rule. It's going to be 2 ohms plus 7 ohms, and that's 9 ohms. And that's it. For everything else, I'm going to use a calculator. For example B, these two resistors are hooked up in parallel. Now, I use the parallel circuit equation for resistors in a very specific way. I like to kind of pre-solve it for the total resistance. So this is another way that you can do this. To get the total resistance of two things in parallel, I would do 1 over the first one plus 1 over the second one to the negative first power. And I don't even calculate anything in the middle. Whether you have a graphing or a scientific calculator, you can do this. So parentheses 1 over 10 plus 1 over 14, end parentheses, and then I just want to take it to the negative first power. So if you have a graphing calculator or scientific calculator, there's an x to the negative first power button, and you push that, and then it gives you the total resistance. If you're doing the parallel circuit resistance rule, you should always get a lower number than your lowest resistor. So I got 5.8 ohms. Cool. The other two examples are the extension, because we're going to start combining our circuits, because that's how circuits are really built. There's very rare situations for like a purely series or a purely parallel circuit. When you look at these last two, you want to make the decision of whether you're looking at what's fundamentally a series circuit or what's fundamentally a parallel circuit, and I'll show you what I mean. This circuit, I would argue, is fundamentally a series circuit, because you have this one, the 3 ohm resistor, and it is in series with this network of two parallel circuits. So here's what we'll do. The equivalent resistance is whatever this resistance is, plus whatever these resistors have in total. So the first thing I'm going to do is I'm going to find that resistance. And I'm going to use the parallel rule. So 1 over 4 plus 1 over 5 to the negative first power. So I start with the parallel because they are part of a series circuit, so 2.2 ohms. And then for the and I can consider the entire thing. So the true equivalent resistance is 3 ohms plus 2.2 ohms, or 5.2 ohms. So you can kind of like philosophize about this. You can say, well, this is a series network. The resistance of this network is going to be 3 plus whatever this is. So it's going to be more than 3, but it's not going to be 4 more than 3. It has to be like less than 4 more than 3. It's kind of a weird thing to say. But because these two things will cause a lower resistance, whatever I get here, I add to this one. Cool. For the one on the right, part D, this is fundamentally a parallel circuit because the big part of it is parallel. The 8 ohm resistor is in parallel with this branch right here. So I solve it in the reverse order. I find the series part. The first equivalent resistance is going to be 6 ohms plus 7 ohms. And I get 13 ohms. Then I go to parallel, because that's the bigger part. I do this, and I say, okay, well, the equivalent resistance is 1 over 13 plus 1 over 8 to the negative first power. 1 over 13 plus 1 over 8, negative first, and I get 4.95 ohms. You probably just round that to 4 or to 5, but you get the point. So at this point in time, if you've watched all of this, you are ready for 9.5, 9.6, and a shot at 9.7. If you are satisfied with how things are going in circuits, you can just work on your project. We'll pick up next class with wherever we're all at. So if you want to work on your project tomorrow, that's fine. If you want to work on circuit stuff, that's fine too. And we will get done. Thanks.